When the State of Israel was officially recognized in 1948, it was clear that there would be huge environmental and engineering challenges to overcome in order to provide water for the rapidly increasing population there. The National Water Carrier of Israel was a mega-project drawn up to redistribute water across the entire land. It was ambitious, technically pioneering, and ultimately essential to the development and prosperity of Israel in the 20th century. But what made it necessary? Who built it? And at what cost? What specific challenges and political backlash did it face? And what is the legacy of the engineering methods and technology used? At the end of the 1940s, the scale of new residents finding their homes in Israel was increasingly dramatic. The events of World War II and the utterly devastating impact that the Holocaust had on Jewish people led to huge changes in the geopolitical map of the planet. To put this into context, in 1948, there were just over 800,000 people living in the region now known as Israel. Only 3 years later, in 1951, the population had doubled to over 1.6 million. And it currently exceeds well over 9 million people in 2025. All of this inside an area of just 22,000 square kilometers, roughly the same size as the state of New Jersey. The main issue for water scarcity in Israel came from the geographic imbalance of its distribution. Areas in the north of the country, such as the Sea of Galilee and the Jordan River Basin, have always been rich in natural water resources, with an annual average of around 40 inches of rainfall. However, in central and south Israel, where most of the new residents were flocking in the late 1940s, it was a very different story altogether. The huge Negev Desert in the south covers approximately 50% of the entire land area of the country, with some places here receiving less than 4 inches of rainfall a year. While there had been Bedouin tribes settled here for centuries, it would become vital for Israel's nation building that a more equitable water source could be put in place to serve the Negev and surrounding areas. Only then could the new residents be suitably accommodated, and Israel be set on a path towards becoming the global superpower that it is today. The water carrier of Israel spans 130 kilometers in a massive network of underground and overground construction. 87 kilometers of steel and concrete pipelines are channeled deep underneath the ground. 13 kilometers of tunnels carved through rocky terrain that previously lay undisturbed for millennia. And it's all supported by 8 kilometers of open canals and a collection of huge balancing reservoirs. Planning began in the early 1950s, driven by the newly established Tahal, a water resource planning company part-owned by the state. Impressively, building took a period of just 8 years from 1958 to 1964 to enable the transit of a staggering 450 million cubic meters of water every day. That meant over 1.5 million cubic meters at peak flow every day. The cost at the time was around $420 million, a figure that would represent a staggering $4 billion today. Importantly, the whole thing was created in a modular way with an eye to the future. The creators understood that the NWC would have to adapt as demand increased and new water resource planning technology was uncovered. That's why the system can now move almost 4 times its initial capacity, with around 1.7 billion cubic meters moving throughout the NWC every year. Perhaps the most important engineering challenge to overcome was how to actually move the water in the first place. It would have to be forced uphill from the north of Israel over mountains, through valleys and across deserts to the central regions and the south. Everything begins at the Sea of Galilee that sits at 213 meters below sea level. The national water carrier then works upwards through a total elevation gain of around 600 meters across the whole network. In order to make it all happen, the Sapir Plumbing Station initiates the flow of water through a 250-meter lift from the Sea of Galilee to the NWC starting point. Then, the mighty Salmon Pumping Station takes over further down the line, using custom-built turbines and pumps to elevate millions of cubic meters of water by another 115 meters at the trickiest point of its journey. Salmon currently passes the water into the Yaakov Tunnel that runs 850 meters long underneath the hills of the village of Eliabun and on to the next phase of the network. Thousands of workers, engineers, and tunneling specialists collaborated for years to find the right solution from Salmon to the Yaakov. That's because the extreme topography of the terrain involved boring through limestone and basaltic rock that can be difficult to navigate through. Furthermore, finding exactly the right gradient of incline for maximum water flow in the tunnel without the need to install extra pumping was another logistical headache. Steel and concrete reinforcements also had to be applied in the 3-meter-wide tunnel to account for the huge water pressure it would be under when operations began, not to mention the extra capacity that they anticipated in the decades to come. All of this was a subterranean marvel created underneath the hills with minimum impact to the ecosystem that continues to thrive on top of them. Two more major pumping stations at Eshkol and Mishmar HaEmek can then facilitate water flow into central Israel, regulating, filtering, and balancing before heading south to the Negev. With such an arid climate across the entire area of the country, water evaporation was to be a key consideration for the overground reservoirs and canals. This particular problem was tackled with several solutions. Physics dictate that larger surface areas would increase the levels of evaporation from prolonged sunlight and occasional wind, particularly over the open reservoirs and canals. To combat this, many of the smaller reservoirs were constructed in oval or circular shapes to try and limit the exposed areas as much as possible. The Eshkol Reservoir, one of the largest in the NWC, holds over 5 million cubic meters of water and was created in a rectangular shape for the same reason. It sits at 400 meters wide at an increased depth of 15 meters. This was a design choice taken because deeper bodies of water evaporate less as they take longer to heat, so a smaller surface area needs more depth to maintain the volume needed for such a huge undertaking. Similarly, the canals were constructed in trapezoidal shapes with variable depths and sloping sides to avoid heat absorption on all their sprawling sections. The success of the national water carrier of Israel radically transformed the urban landscape of Israel, with towns such as Be'er Sheva in the Negev becoming a globally recognized hub of education, research, and industry as a direct result of its success. Arad, also in the south, became the country's first planned city in 1962 and prospered quickly despite its location in the harsh desert next to the Dead Sea. All because of the opportunities offered by the NWC. Towns like Dimona, Mitzpe Ramon, and Krayat Gat followed suit, with extensive development that can only be fostered by a guaranteed and usable domestic water supply. The national water carrier of Israel was not without controversy, however, with concerns and opposition that were even cited as factors in the infamous Six-Day War that broke out in the region in 1967. Neighboring countries, including Jordan, Syria, and Lebanon, had raised concerns that the activity around the Sea of Galilee would have an effect on the shared water levels of the Jordan River basin area. A concern that was eventually realized with a significant drop in levels from over-extraction. This drop led to environmentalists accusing the national water carrier of harming the flora, fauna, and water quality, with an overall degradation for the lower River Jordan. Interestingly, it could be said that the appearance of a new technology that would eventually come to use the existing NWC infrastructure went a long way to alleviating the concerns for shared water resource management. The process of desalination had been piloted in Israel since the 1960s for industrial use. Typically, this is done through a process of reverse osmosis, where seawater is filtered, then forced through semi-permeable membranes at high pressure. Only water is passed through the membrane, separating the salt, minerals, and other impurities from it that can be safely distributed back to the sea. This method can often recover up to 50% of the feed water as fresh water. Since the turn of the 21st century, Israel invested heavily in the desalination process, with custom-built plants appearing all over the country's Mediterranean coast. It worked to such an extent that around 70 to 80% of the country's domestic water supply is now from desalinated methods, whereas previously 100% was fresh water using the NWC. However, all of these plants now feed their water directly into the NWC to distribute it. This represents a wonderful, lasting legacy for a project that was as iconic as it is inspirational. Large-scale schemes such as the California Water Project in the United States, the South-North Water Transfer Project of China, and the Great Man-Made River of Libya all owe the national water carrier of Israel a debt of thanks for its pioneering use of distribution and drought avoidance techniques. It remains the standard-bearer for man's ingenuity in redistributing the most vital element required for development across the widest area possible, ensuring that terrain, climate, and even distance would never be insurmountable barriers for access to water in a rapidly developing nation.
Remember to hit the subscribe button and ring that bell to stay updated with our latest content. And while you're here, why not check out another one of our exciting videos? Thanks for watching, and see you in the next one.